Okay, that's it.
Action. My pleasure to introduce Carl Malberg from LSU. We'll talk about percolation probability and partitions. There's more to the title, but I don't have the sheet in front of me.
Yes, thank you. The other part of the title was Unexpected Applications of Number Theory, which I just didn't feel like writing, but of course is important because I am supposed to be, well, I am a number theorist by training and practice of techniques, if not always results. And that's what I hope to and plan to illustrate in this talk, that using some of the very detailed analytic techniques that number theorists have developed over the centuries, one can often apply these and find some unexpected uses to problems arising from seemingly very different parts of mathematics. So this is meant to be a true colloquium. It should be friendly and accessible, well, or accessible anyway, throughout. And these three words and the title on the board should mainly go in thirds along the talk. So if you don't like one section, then 15 minutes later, pay attention again, because there will be something new that perhaps you will like. And this is part of an ongoing sequence of research projects. There have been 2 publications resulting from this, and I like to throw out references at the beginning of a talk that I give. It looks like thus far you're all very polite. There are no cell phones or tablets, well, okay, 2 or 3 on the table. And actually, I don't mind that. When I'm in the audience, I frequently have a cell phone or a tablet or so on. And if I am lost or losing focus or interest in the talk, if I have a name or a title or a paper reference, then I'll look that up. So I will just assume that if anyone is looking at a little screen, you've gone to my webpage and you've pulled up one of these 2 references as you want to follow along. So without further ado, here is bootstrap percolation, which is the motivating question for this collection of ideas. And I'll talk about where it came from in a moment, but first just let me set the stage. So in bootstrap percolation, there are cells. We're working in some graph or lattice, some crystalline structure. Could be in whatever dimension, but let's just say 2-dimensional. And each of these cells or nodes or whatever are considered to be a site, and they can see each other, they're neighbors. And there are 2 states. Cells are either active, which I'll shade in, or inactive. And I'll just for, well, both simplicity and because it was one of the original motivating examples and appears in some of my work, I'll just think about a square lattice. So let's actually take a perfect square lattice, L by L, possibly infinite. L could be infinite. And there's an initial configuration that will generate through an independent Bernoulli process, where each cell will be set to, randomly and independently, will be set to be active or inactive with just some fixed probability. So let's say the cells are active with probability p and inactive with probability 1 minus p for some parameter p. And so you get some configuration of active and inactive cells. don't know, maybe like that. And this is a little bit of mathematical culture and a tangent, but it bears mentioning because whenever one can flag a Fields medalist in a talk, it's maybe worth doing. So this would be the end of the story if my talk were about bond or site percolation, which are two names for the same thing, just depending on whether you're thinking of the graph or its dual. You would ask questions like, say, in the infinite case, is there an infinite connected component of active sites? An infinite connected active component. An infinite cluster of black squares. Or other questions like, is there a solid black line path from the left to the right? I won't write this question grammatically, just active path left to right. And the answers to these sorts of questions were the subject of Smirnov's work, which was part of his Fields Medal citation in 2010. And the answer to the first question, anyway, turns out to be that there is a sort of a critical probability, so some PC, such that the answer to this question looks something like this. So if you wanted the probability of an infinite active component, then below the critical probability, that probability is 0, and above it, it ramps up, well, something like this. That's roughly the sort of framework. And actually, particularly in a triangular lattice, there is a beautiful story with something called conformal invariance, where basically in the infinite limit, you actually start seeing like fractal shapes that have just some continuous properties. If you look at, say, the boundary traced out by the active versus inactive sites. But that's an aside, because in bootstrap percolation, there is a further evolution. There is a growth rule such that you should really think of this initial configuration as some initial infection or spark of a fire or spreading of some initial cancerous cells in some biological setting. And then this infection tends to spread. And maybe the simplest, there are a variety of growth rules that are interesting, but the simplest one is just the 4 nearest neighbors, that if you have at least 2 active neighbors, any 2 of them, so it could be the corner adjacent, that is enough to flip on that inactive cell in the middle. And this is a much simpler automaton than the game of life, say. There is no depth. There's just only spreading. You spread and spread and spread until you can't any further, and that's the final configuration. And you can ask similar questions. Let me, before I forget, return to the motivation for the bootstrap percolation model. So the bootstrap percolation model is actually a limiting case, a high temperature limit of the famous Ising model for induced magnetism, for ferromagnetism. That if you have a metallic structure, a metallic crystalline lattice, then this is kind of the process that describes how it becomes magnetized and oriented. It's this sort of local spreading. It turns out that bootstrap percolation is also used to model these sorts of spreading phenomena like I described, or one of my favorites, it's used in the study of crack propagation in things like glass. You can think of these as being like impurities in the manufacturing process, and cracks are going to tend to spread along those weak points from the impurities. And this model was introduced in the 40s, more or less. So you can ask then some similar questions, or I'll just say one similar question in the, oh, so why don't I quickly run through the example of what it would look like if you ran the bootstrap percolation process on this initial configuration. So that cell would fill in, and now those two corners, and it'll get this entire lower left bit. Now we can jump that gap, get all of these. And if you continue, this will actually fill in the entire L by L square. That's sufficient initial configuration to do so. And the reason I wanted to work through that example before asking this question is because that's a question I want to ask here. So let's ask an even stronger question than just an infinite connected active component. Let's ask, what is the probability that the entire L by L square becomes active at the end of the process? And there was some history to this problem. A number of experimentalists, both physicists and statisticians, published papers with estimates of a critical probability for the bootstrap percolation model. So from the 50s through the 80s, there were a variety of papers where they would run various simulations, say on a 10,000 by 10,000 grid, and then find estimates for a similar looking critical probability with some error bound, using some sort of statistical fitting. And therefore came, actually that ceased in the 70s, so just forgetting this next reference. It was therefore a bit of a surprise when the actual answer was produced by some mathematical physicists, Arnoud van Enter and Roberto Schoenman. Actually, there is no critical probability, or rather there is, it's just trivial. It's 0. In other words, if you pick any fixed positive probability of initial infection, and you let the size of the square length go to infinity, then the probability that the entire square becomes active goes to 1. So there is no interesting cutoff. This is somehow a very hungry spreading process. You give it an inch, it takes a whole L by L square. And this is actually pretty hard to observe. Even now, even if you run this on 1,000,000 by 1,000,000, it's still very hard to observe the true large-scale behaviors. This is taken now as a very striking cautionary tale. Even with L around 1,000,000. Okay, so if there is no fixed critical probability cutoff, then let's define a refinement. And, well, I'll put up this definition, but then I'll say the keywords that really give it away. So the finite scale critical probability is defined as P sub C of L comma K, that's just the notation, and here is the definition. It's the probability, or rather, it's the smallest probability, so the infimum of all little p's, such that the probability that the L by L square becomes active is at least a half. There's nothing special about a half here. Actually, in the limit as L goes to infinity, this is actually a 0-1 event, meaning that if P is in a larger range, then this probability goes to 1. If P is in a smaller range, it goes to 0, and the range in between is negligible. Maybe I won't bother writing that, but just this half could be anything.
What's K?
Oh, thank you. That's not so important, except I'm going to state it in theorem, so.
Is it 2?
K is 2 in terms of everything I've drawn on the, yeah. I was doing so well with my board work, and now I start to destroy it. So, since this is for posterity, let me draw this again. So, one slight modification or generalization of this model, though there are many other shapes that one could also consider, but in this talk, I'll talk about K minus 1 cross, where these arms stick out a distance of K minus 1, and the growth rule says that if you have at least K active sites, that leads to an active center. This is not the only convenient case, but the geometry is pretty nice here, so we'll turn out to talk about it today. So that's this K, yes, and everything I drew before, K was 2. And the big result that really started bringing this on the more precise and formal ground is that this is actually a process that exhibits metastability, or equivalently has finite size scaling, or equivalently has a power law or satisfies a power law distribution. These are all phrases that basically mean the same thing, but they're just used in slightly different settings. And a quantification of that is the following theorem from the mathematical physicists Michael Eisenman and Joel Leibowitz in 1988, that there exist two constants, alpha and beta, such that this critical probability for the case k equals 2, this original bootstrap percolation model, is asymptotically of order 1 over log L. So this asymptotic notation simply means that for a sufficiently large L, this is true. Maybe we can just write it that way. And so note that as L goes to infinity, this critical probability does indeed go to 0 in the way I mentioned here.
Beta is constant in L, isn't it?
Yes. And the first theorem of my own that I will present comes from a collection of papers that I know I'm just going to throw together into one theorem. Various people were responsible for various parts. So in my paper that I mentioned from 2012, a paper of Janko Grabner, Alexander Holroyd, and Robert Morris from 2013, and a paper of Holroyd, Tom Liggett, and Dan Romick in 2004, says that actually we can refine this. Here is the main term for the critical probability, where lambda k is a constant. I'll specify in just a second. And here is the error term. Where this is a little o of 1, which just means, if you like, you could just replace it by an arbitrarily small constant, like a delta, just for any delta greater than 0. And here, this lambda k turns out to be minus 3 pi squared, or sorry, the 3 goes on the denominator, minus pi squared over 3k times k plus 1. So a couple of comments about this theorem. It's this pi squared over 3k over k plus 1 that really caught my eye as a number theorist. So this is kind of what got me interested, or thinking that there might be something to do in this world. For example, so with this percolation model, I'm only considering k at least 2, but if you ignore that for a second, lambda 1 is pi squared over 6, which is a special value of the Riemann zeta function, zeta of 2, Gauss's famous evaluation. Another comment is that this error term differs from the main term by log L to the 1/2, which grows very, very slowly. That's actually kind of the explanation for why this is so hard to observe experimentally. Like, even when L is 1,000,000, the square root of log of L is not very big, and it's not very distinguishable from log of L. So it's very hard to actually see that main term. Note that another way of thinking about these statements is, so I just erased the picture, is that the interesting region is when L is approximately e to the lambda k over p. That if you wanted to start with the probability, which is equally plausible, thinking in terms of the real world, like you had some error percentage, or some tolerance in your manufacturing process for that glass pane, then here is how big of a glass pane you can make without having major problems with cracks, in a rough statement. And let's see, I guess.
It looks like you're saying lambda k is negative, but you didn't mean that, did you?
Oh, no, I'm sorry. Of course I didn't.
Good. Just check. Sorry, go ahead.
Yeah, of course not. Thank you. And in this theorem, I guess my contribution was, so it was actually proven as two inequalities, and my contribution was the greater than or equal to part of it. So let me say something roughly about the proof ideas for how bootstrap percolation really looks. So one of the big technical achievements here was a paper of Alexander Holroyd. So, of course, a minimal sort of configuration that will eventually become active would just be a fully diagonal like this. If you ran the bootstrap percolation process, and I'm only going to talk about the k=2 case like this picture from now on. So this would eventually fill the whole square. But that actually turns out to be too specialized, requiring that specific diagonal configuration. These are just too rare to matter. They're not the dominant effect. So this does become completely active, but it's very rare. But there's a little bit of a modification of that, where you take diagonal stair-step rows and columns, and if it's now the case just that there are no two adjacent empty columns, so fill in this lower left, and then we'll say the second column were empty, and there would have to be something in the third column. The fourth column's empty, there's something in the fifth column. And similarly with the rows. So say the first little row were empty, but then there's something in the second one, and so on. You know, at worst, they alternate empty, non-empty. It takes a little thought, but you could work it out, even in your head, just try to fill it in this picture. That actually does eventually become active. And through some extremely intricate combinatorial probability, so this is already a lower bound then for the configurations that will eventually become active. Here I've given a family of configurations that do become active. There's some very intricate combinatorics that show that this is roughly also an upper bound, in the sense that any configuration that does become active is somehow either equivalent to this or dominated by this. This is somehow the case that matters. So this sort of configuration is really what controls this is the cutoff as to whether your configuration becomes active or not. So this is the key configuration. And this paper is kind of a tour de force of combinatorial probability, and it uses every single letter of the English alphabet at least once for some variable or another.
Carl, does it matter that these are squares, or can they have different shapes?
So it does matter. There's a variational principle that if you had, that I'm not going to go into, but say that you had an L by L square, and as compared to a rectangle whose perimeter was also a total of 4L, then just given the way that the probabilities line up, in short, let's say you would have a bunch of short, fat columns, that would somehow be much rarer than having these columns and rows that are both steadily growing. There's a variational principle there.
Because I was thinking about the paramagnetic example you mentioned. I mean, they are not really squares, the structure inside.
Yeah, sure.
Not
I mean,
necessarily.
this is,
Yeah.
yeah, that's of course right, and the story changes. If you do unwind and go back to your physical motivations, of course there is additional geometry that comes into play. But for this toy model, which is now abstracted, this is all correct. Anyway, so I don't want to belabor this percolation portion of the talk, and no, I am not planning on taking an hour and a half here. This always was intended to be the longest third, so. Anyway, just in case you know some lattice combinatorics very well, which I know a couple of you in the audience do. So the proof and characterization that Holroyd gave, like, the tricky part is about correlation and independence in some sense. So there are a variety of combinatorial inequalities like the FKG or the Vanderburg-Kesten that will measure the disjoint probabilities, the probabilities of certain events occurring disjointly. The motivating example is something like, well, say that you were in a graph and you knew that you had a connected path from this node to this node. That's information that has an effect then on whether there's a path between this node and this node. If you have more edges in the graph, that has an effect on other paths. And all of this kind of comes into play here, right? talk too much about that. Another component of my part of the proof has to do with Markov processes with slowly varying parameters, which is what I'm going to speak about next. And finally, a bit of number theory, in particular, some asymptotic expansions from number theory. The technical words would be the cuspidal limits, of automorphic forms or elliptic theta functions. And I'll close with that. That will be the last and the shortest section. Okay, so changing gears, though we'll tie it back to percolation in a moment. Here's probability. And the probability of certain pattern avoiding sequences. So consider independent events, x1, x2, possibly infinitely many of them, so let's just list them all out like that, where each event has two outcomes. It's positive or negative, or I'll just say A or B. So it's A with probability uj, and B with probability 1 minus uj. So here is a certain technical bound that I'm just going to state. This is also found, at least in one version in my paper with Bringman. And then I'll talk about the motivation for this after I'd stated it. So if these probabilities, U1, U2, and so on, are monotonically increasing, and we'll cut off at some possibly infinite n, so we either cut off or go out forever, then there is a bound for the pattern avoiding sequence that you look at the events x1, x2 up to xn, and that you never see the pattern b to the k. You never have k consecutive of these events that all output b. So you flip a coin 100 times and you never see 6 tails in a row. That sort of thing. And that would actually be a special case, though not a very interesting case, of this theorem. Then there's a lower and an upper bound. The lower bound is a product of some little fk 1 minus u sub j. The upper bound is the same thing, except now the product starts at k rather than 1. But again, fk 1 minus uj, where this fk is a function. Fk of x is the unique positive decreasing solution to the functional equation f to the k minus f to the k plus 1 equals x to the k minus x to the k plus 1. That's a mouthful, admittedly. So first of all, you know one instance of this theorem. Actually, you know the k equals 1 case. If k equals 1, it turns out that f1 is 1 minus x, and the probability that you have no b is the same as the probability that every xj is a, and that's just simply the product of the probabilities of each a occurring, like so. And that's just plugging in 1 minus u sub j to 1 minus x. Okay? So it's a very complicated way then of writing this fact. But what's really going on here is that if every u were the same, then this is actually something from the theory of linear recurrences. Oh, it looks, make sure I get the details correct. So if you let p sub k be the probability that this condition is satisfied out to, well, the nth argument, here n plus k, so this is just shorthand for this probability, then there's a simple recurrence. That is explained in the following way. So if you don't want to have any b to the k, then at the end of your sequence, you could end with a, you could end with ba, or maximally you could end with b to the k minus 1 a, but you couldn't have had any. Sorry, I proposed incorrectly. Ending, you could end with A, you could end with AB, or you could end with at most k minus 1 B's. And this is a linear recurrence of the sort that you might teach to your undergraduate combinatorics class. So to solve these, right, you simply pull off the characteristic polynomial, which basically comes from assuming that you have an exponential solution, and that's exactly what this f is. So f sub k of 1 minus u is the largest in absolute value. So that part is actually a little deeper. That follows from the, if you like, from the Perron-Frobenius theorem for Markov processes or matrix transformations, is the largest solution of the form pk of n plus k equals, rather, pk of n equals, say, some gamma to the n. So fk is just the largest possible gamma that goes in this. And it happens to satisfy this functional equation that just pops out in a bit of algebra. And so that's what this theorem is. It's really an interpolated version then of a linear recurrence, where not every one of these is a u, but they are actually u sub n's and u sub n minus 1's and so on. So the theorem is an interpolated, the theorem interpolates linear recurrence solution. Right, if all of the u's were the same, you would just have this power. And so for each of the actual u values, then you just pull one instance of this particular eigenvalue of that system. There are one or two other comments. You might wonder about this condition that the u's be monotonically increasing. So a remark on that. If n is infinity and the u sub j's do not go to 1, then the theorem statement is trivial. The theorem statement would just be 0 is less than or equal to 0 is less than or equal to 0. So the point is that this monotonically increasing case, certainly in the infinite setting where n is infinity, this is the only interesting case. The inequality of only zeros is not so interesting. So, I won't say any details, but actually in those two papers, there are two different proofs of this theorem. And the first one, it's basically through some rather intricate calculus and theory of convex functions, multivariable calculus. The second paper, I like the proof much better, that actually uses Markov chains, and you heard me saying the words eigenvalues. That's how I now properly think of this statement. So to tie this back to bootstrap percolation, note that if u sub k were 1 minus q to the k, where q is 1 minus p, that original p, which is a method to this madness, though I apologize for how it looks at the moment, then the probability that x, sorry, I don't want to abuse k's, if u sub j is 1 minus q to the j, then the probability that this random variable xj is a is then 1 minus p to the j. That is exactly the probability that a column of height j is non-empty. Because 1 minus p to the j is the probability that a column is completely empty. So its complementary is the probability that it's non-empty. And so actually, this sequence condition where I have no bk's, that's exactly measuring this combinatorial condition, that there are no adjacent empty columns or rows. So I'll introduce a small bit of notation, pk of q. Let this be the probability that there are no bk's in the xj's, and now I'm taking the infinite case, and I'm setting uj to be 1 minus q to the j, as I described. That's, in other words, exactly the probability of having one of these stair steps. then the theorem is that logarithmically, this pk of q is asymptotic. Now it's a minus sign. I've gotten ahead of myself. Minus lambda k over s, as s goes to 0, where I'm writing q is e to the minus s. It just turns out to be, you could equivalently rewrite this as q goes to 1 from below, but it's slightly more convenient with this s. And it's that same lambda k as was in the main percolation theorem. That's not an accident. And this proof actually follows from the theorem to its right. In particular, the log of pk of q is approximately now the integral. The sums become an integral from 1 to infinity of the log of fk of, say, 1 minus u du, which turns out to be exactly, after a change of variables, it turns out to give exactly that value. That's not a completely obvious evaluation. There are some tricks with dilogarithm and some of its symmetries. But the brief upshot is that this percolation probability is bounded and approximated by these technical estimates. Okay, so I don't want to test anyone's patience. I don't know what your standard is here. I'm at 50 minutes. I would be very happy to have another 5 minutes or so, but cut me off if need be.
It's okay with me? Another 5 minutes? Yeah.
Great. I will not abuse.
I assume you're going to talk about partitions then?
Yes. Squeeze in a couple words about partitions. And I'm just going to spend.
So these are asymptotically decreasing sequences of time.
Indeed they are, yes. In fact, I have an infinite number of topics. I'm not sure if my time function is convergent. So we may need to truncate. Anyway, so partitions. This pk of q, if you like, can be written out in like a very stupid and naive way. It's just the sum over all infinite sequences of xj's that are, each individual xj is either a or b, and there are no adjacent b to the k's. And whenever xj is a, you multiply by 1 minus q to the j. That's kind of the weighting that's coming about here. And whenever the xj is b, you multiply by a q to the j. You'll see actually that you can only ever have finitely many b's, which, or everything else ends up having measure 0 or vanishes in the formal power series ring in Q. That's, if you're thinking analytically, where Q is some real value, that's just a consequence of Borel-Cantelli. But doesn't matter so much. Anyway, there's some combinatorics that I'm not going to bother with at all. It just turns out that due to Holroyd, Liggett, and Romick, it's kind of an unexpected and very cute combinatorial identity. If you take this product, 1 over 1 minus q to the n, which is the generating function for integer partitions, I'll come back to in just a second, and multiply that by pk of q. That actually turns out to be the generating function for little pk of n, where little pk of n is the number of integer partitions of n with no k adjacent parts. And of course I haven't defined what an integer partition is, and I don't want to talk too heavily about this adjacent parts thing. So I'm really going to close by just talking about how asymptotic analysis plays a role in the theory of partitions. So I'm really just going to talk about Euler's partitions, and then I'll close with a call out to Hardy and Ramanujan. So the introduction of the theory of integer partitions is that this infinite product of 1 over 1 minus q to the n is the generating function for p of n q to the n, where p of n is the number of partitions lambda of n. That's a symbol that means partition of n. It's best illustrated just by example. So p of 4 is 5, because here are the ways that you can additively decompose in a weakly decreasing way 4 as a sum of natural numbers. These are the 5 partitions of 4. So this is a beautiful and fascinating function. It has both arithmetic and analytic interests. It has both divisibility and congruential and p-adic properties, but it also has asymptotic and analytic properties. It's been one of the richest sources parallel to the development of number theory, the analytic number theory in the 20th century. It's always a test case to see if you can prove something new and more about partitions. The reason in one sentence is that this happens to be a meromorphic modular form. It's 1 over an elliptic theta function, if those words mean anything to you. Anyway, so here is a famous theorem of Hardy and Ramanujan. It says, well, how many partitions are there of n? There's not a simple formula that is an exact formula, but here is an asymptotic formula. So it's a super polynomial, exponential in the square root of n. So that's quite a lot of them, though it's not exponential in n. And the proof, or one proof, this wasn't Hardy and Ramanujan's proof. They invented something called the circle method. But another proof follows from a Tauberian theorem that is maybe going to be more obviously relevant to what I'm talking about here. That it turns out that this product is asymptotically behaves. So, well, before I write anything down, let's stare at this for a moment. And I'm going to look again at this limit as q goes to 1. So this has an essential singularity as q goes to 1. Right? It's a product of a countable number of terms, every one of which has a simple pole as q goes to 1. So this is an essential singularity overall. So how fast then is it really growing? What does it look like? And the answer is this. it's exponential, so there's some stuff out front, doesn't matter so much. And then it's e to the pi squared over 6s. So this is the nature of the essential singularity. It's exponential in the inverse of s. Or if you like, the s could be replaced by 1 minus q. And the reason I wanted to highlight and end on this note is because that's a very similar sort of calculation that we ended up using for the bootstrap percolation. This is a small glimpse at techniques that I use and some of how these limits are tied to number theory and why they live in my world. So I'll close there. Thank you.
Question?
So these techniques that you use that come from number theory, how do they arise in number theory? I guess that's a pretty general question, so you can just pick one.
I'm not even quite sure what you're asking. Like, for example,
Well, the people, so these methods that you're using were invented to answer some sort of number theoretic question, right?
Yeah.
So what sort of question?
Oh, okay. So for example, the circle method, which Hardy and Ramanujan had one version, and when they were studying the partition function, this was actually the first time that this version of the circle method was used. But another example would be the Hardy-Littlewood circle method, which was introduced specifically to address the number theoretic problem of Waring's problem, which is stated simply, how many ways can n be represented as a sum of squares, or cubes, or fourth powers, or so on. And roughly the way this works is you can take the Diophantine question that encodes the statement that n is the sum of squares, and you can put that into a generating function, a Fourier series, and then do some Fourier analysis and some contour integration on that generating function, and that is the circle method. And the circle method is also used in things like character sums, like short intervals of character sums. So, for example, if you take the Mobius function, which is standard in elementary number theory or in lattice theory. So, for those of you who maybe don't know this, mu of n is an alternating indicator for the number of prime factors if n is square free. So n is just the product of distinct primes. So P1, P2, and so on up to PR, where they're all different primes, and it's 0 otherwise. This is very relevant in elementary number theory. And it's a fact that if you sum this up, it's a fact that if you take it as a divisor sum, then it's 0. But other questions you can ask are, how does it alternate? So what if you just take n from 1 to some large capital N? So this alternates between -1 and 1, and sometimes it's 0. And so You know, is there cancellation? Do you see cancellation? And the answer to this question is something you can get a handle on analytically, again, using something that looks very much like the circle method. And once you have the answer to this question, that's one way of proving the prime number theorem, actually.
Anything else? Thank you again.